We are back with some more counting. So we're going to be talking about something called permutations. And really what this boils down to is, let's say we've got 5 blocks or 5 books or whatever rectangular objects your heart desires. We have 5 of these. We're curious about how many different ways can we order these blocks. And it just goes back to the fundamental theorem of not calculus, sorry, wrong class. Fundamental theorem of counting. Right? We just look at things in order. Let's say for our first block, how many choices do we have for our first block? We have 5. Right? We can grab any of these blocks for the first block. And then the second one, how many choices do we have? Well, I don't know what we chose, but we chose something here. So we only have 4 choices remaining, and so on and so forth, right? There's 3 for the next, 2 for the next. And by the time we get to the last block, there's no choices left, right? It's just the only block that remains. So this might look familiar. We are going to multiply all these up. How many ways are there to order these blocks? 5 factorial, which is, I believe, 120. Yep, there are 120 ways of ordering these blocks. So most of you have probably seen a factorial before, but for those of you who have not, let's say that we have an integer. So n is some kind of integer, and let's just say it's at least 0 for now. Then n factorial is just n times n minus 1 times n minus 2, and so on, all the way down to 1. And again, it's pronounced n factorial. It's just an exclamation point, right? So this is like 5, and then you subtract 1, so you multiply by 4, and then you subtract 2, so you multiply by 3, all the way until you get to 1. That would be 5 factorial. So for example, this is 5 factorial. So this is at the heart of permutations. It's really just the fundamental theorem of counting. But now, right, instead of just doing, thinking about 10-digit pins, how many different ones are there? Well, now we're not able to, replace, essentially. So if you did, a 10-digit pin, and you couldn't use the same number twice, then it would be like a permutation. That'd be probably a partial permutation, which we'll get into later. But anyway, let's do another example. So let's say that you're designing some brute force algorithm to unscramble words. The question is, how many combinations might you have to go through? Let's not talk about on average, but what's the most amount of combinations? What's the total number of orderings that you might have to go through before unscrambling something and getting to the word melon? Well, it's really the same thing. Each one of these is like our little blocks, right? Here's our red block, and here's our blue block, and then we got the green block, and and so on. This is just the same exact problem. We have 5 things. How many orderings are there for those 5 things? It's still going to be 5 factorial. All right, it's 5 times 4 times 3 times 2 times 1. It's still 120. It's the same problem as the last one. It's kind of an isomorphism in a way, right? Not a technical application of that word, but remember when we talked about graph isomorphisms, it's like, this is the same graph just with different words, just different name, different locations. Mathematically, it's the same. So these 5 letters and those 5 blocks are the same. All right. And again, this kind of only works if there are no repeat letters. There are repeat letters, and it becomes a slightly harder problem. So let's say we have a longer word. I think there's no repeat letters in here, but if there is, you let me know. That's kind of an interesting question. What's the longest word that doesn't have repeat letters? This might be close. Ambidextrously. All right, well, how many ways are there to do that? Well, we got the first letter. So for the first letter, we have how many choices? We have to count how many letters there are in this word. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 letters, I think. So the first letter has 14 choices. And then the second letter, there's 13 ways of doing that. And then the next one is 12. And of course, we know how this is going to go all the way down to 1. This is 14 factorial. I did not have my calculator ready. I should have. What is 14 factorial? It is 8, 7. I'm going to use scientific notation. It's 8.718 times 10 to the 10th, roughly. All right, so that's approximately what it is. So what is that? That's like 8718. That's 3, 4, 5, 6, 7, 8, 9, 10. That's like 87 million approximately. So quite a few ways of ordering this. All right, so let's say that you were doing some kind of algorithm for this. You might have to do this loop 87 million times. Well, it'd be loops within loops, but you'd essentially have 87 million steps, at least. So the point of this is that factorials grow really fast. They grow faster than exponential functions. All right, so they grow super duper fast, and we could kind of really show that. You may have heard this before. You may have heard just how big this is. But if you think about the number of ways a deck of cards can be ordered, how big of a number do you think that is? Well, there are 52 cards in a standard deck. We're not talking about jokers or anything. So the top card has 52 options. The second card has 51 options, and so on and so forth. 52 factorial. This is 14 factorial, and that was 87 billion, I think. How big is 52 factorial? Well, the book comes in and saves the day. The book writes it out for you. How big is 52 factorial? This big. This is how many ways there are to order a deck of cards. Now, there are many sweeping pictures of what that means. It's a big number, okay? It's a big number. So factorials grow really super duper fast. And that's the point of this, is when we do permutations, if we have bigger things, think about computational intensity, think about memory constraints. When we're looking at permutations of very large, not even large, right? 52 is not a super big number, okay? But just something to keep in mind as we're talking about permutations is size. These things can get huge, okay? So I'll leave you with that. And in the next 2 videos, we're going to start introducing a few algorithms that you can use to enumerate permutations.